Hello. The first section builds on an identity involving triangular numbers that was presented in our previous video, triangular numbers and Hurwitz's theorem. Deriving first a general identity for all polygonal numbers, followed by a broader generalization involving sum of polygonal numbers. The second section extends the two squares and two triangular numbers identity discussed in our previous video, examining the few cases where prime representations of different forms hold. Finally, we present three general polygonal number identities that can also provide prime representations. In our previous video, we introduced a surprising identity which reveals an unexpected connection between the sum of triangular numbers and the sum of squares, a connection that rhymes with the consequences of Hurwitz's theorem. Recapping, for n equals 2, the identity becomes twice the sum of triangular numbers 2a, 2b, and 2c plus 1, equaling the sum of four squares involving linear combinations of a, b, and c. By setting x equals minus a plus b plus c, y equals a minus b plus c, and z equals a plus b minus c, we arrive at a more compact expression where now on the left-hand side we got the sum of triangular numbers y plus z, x plus z, and x plus y, while on the right-hand side the squares x, y, z, and x plus y plus z plus 1. This identity not only covers all integers when x, y, and z are allowed to be negative, but it also bridges two classical landmarks of number theory, Euler's four-square theorem and Gauss-Oreca theorem. Furthermore, this form admits this fully symmetric expression where the underlying symmetry arises from a beautiful and most likely rediscovered identity. What's more interesting is that this identity can be generalized to all polygonal numbers. The sum of polygonal numbers y plus z, x plus z, and x plus y equals the sum of polygonal numbers x, y, z, and x plus y plus z. Though the identity can be manually confirmed by expanding the terms, see the first few polygonal numbers, triangular numbers, squares, pentagonal numbers. To generalize the identity, we can now use the formula for the nth eugonal number. This expresses each eugonal number, for u bigger than 3, as a linear combination of triangular numbers, allowing us to leverage the verified triangular case to extend the identity to all higher eugonal numbers. To verify the general identity, we apply the formula to each term and then group those containing the factor u minus 3. The remaining terms correspond to the previously verified triangular case, allowing us to cancel those terms on both sides of the equation. We can then divide both sides by the multiple u minus 3, leaving the same structure of triangular numbers, but whose indices have minus 1 as an extra term. Using the known symmetry of triangular numbers, we rewrite each term with negative indices. So, when allowing x, y, and z to take negative values, we recover the original triangular identity, confirming that the shifted version also holds, and with it, the generalization to all polygonal numbers. The identity above can in fact be extended even further. To illustrate this broader generalization, let's first look at a few examples using square numbers, as they offer a simpler setting for exposition. When working with three variables, there are three square terms involving a single element, three square terms involving a linear combination of two elements, and one square term involving a linear combination of all three elements. We can expand the identity to four elements, which involves four square terms for a single element, six square terms for two elements, four square terms for three elements, and one square term for four elements. Same happens when expanding the identity to 5 elements, 5 square terms for a single element, 10 square terms for 2 elements, 10 square terms for 3 elements, 5 square terms for 4 elements, and 1 square term for 5 elements. By defining S sub n choose n minus k as the sum of n choose n minus k polygonal terms that combine a linear combination of n minus k elements, we simplify the notation and establish a broader generalization of polygonal number sums. Including the case n equals k gives S sub n choose 0 equals 0, since no elements are involved, allow us to achieve full symmetry in the general identity. Bringing these examples together, we arrive at this general identity. The sum of S sub n choose k for k even equals the sum of S sub n choose k for k odd. To present this broader identity, we illustrated a few examples using square numbers, as they offer a simpler setting for exposition. We have already demonstrated the generalization for 3 variables. The case for 4 variables is just as straightforward as that for 3, as explained below. However, providing the general case for n variables requires addressing each particular case individually, which we won't pursue here as it would be redundant. We start by presenting the identity for 4 variables with triangular numbers, which can be verified manually. Then we can reach a generalization to all polygonal numbers when recalling the formula for the nth eugonal number. This expresses each eugonal number as a linear combination of triangular numbers, allowing us to leverage the verified triangular case and its counterpart when allowing negative values for x, y, w, and z, and so extend the identity to all higher eugonal numbers. Besides the general polygonal number sums identity, loosely connected to elementary symmetric polynomials, there can be determined a few special identities that exhibit some partial symmetries. Consider the case for n equal 4. Besides the general identity, all coefficients equal 1, there are combinations of coefficients a, b, c, and d that satisfy the equality. These are the very first few cases. Notice the pattern. If a sub I, b sub I, c sub I, and d sub I holds, then the reverse combination d sub I, c sub I, b sub I, and a sub I also holds. This symmetry arises because when adding them, if a plus d equals b plus c, then all positions share the same value, which is simply a scalar multiple of the initial solution where all coefficients are 1. Therefore, a plus d equals b plus c is a necessary but not sufficient condition when I is bigger than 0. Some identities can also be established when quadratic terms are involved. Notice the similarities within these structures as well. Here, you can visualize some of the linear and quadratic identities for case n equals 5. And here, the linear identities for case n equals 6. In conclusion, we proved that the identity involving triangular numbers presented in a previous video can be extended to all polygonal numbers. The identity can be generalized even further by S sub n choose n minus k as the sum of n choose n minus k polygonal terms that combine a linear combination of n minus k elements, simplifying the notation and enabling a broad generalization involving sum of polygonal numbers. Besides this general identity, we presented a rich variety of linear and quadratic combinations specific for every n, yielding identities that exhibit elegant and suggestive symmetries. In our previous video, we derived an identity that expresses all odd integers representable as sum of 2 squares in the form 4n plus 1, where n is the sum of 2 triangular numbers. Here, x and y have opposite parity. Since primes of a form for n plus 1 are representable as sum of two squares, a natural next step is to explore whether similar representations exist for primes of the forms 2pn plus minus 1. This turns out to be true for a series of cases. For 6n plus 1, it is already known that such primes can be written as x squared plus 3 times y squared. Below, we present an identity that fits that pattern, displaying a sum of triangular numbers on the left-hand side. The representation requires that a and b have same parity, and that either a or a plus 1 be divisible by 3. But it works too for a minus 1 be divisible by 3, since we can derive an analog identity. So for primes 6n plus 1, the divisibility condition implies that 3n is expressible as a sum of triangular number plus 3 times another triangular number. To present the identity more neatly, we introduce new variables. Let x equal a plus 3b over 2 plus minus 1 and y a minus b over 2. Solving for a and b, we obtain a equals x plus 3 times y minus plus 1 over 2 and b equals x minus y minus plus 1 over 2. Substituting this into our original identity yields another identity that allows mapping all x squared plus 3 times y squared as 2 times the sum of triangular number plus 3 times another triangular number plus 1. Since we're dealing with primes represented as x squared plus 3 times y squared, x cannot be divisible by 3. Hence, n is congruent to plus minus 1 modulo 3, matching the requirement in the first triangular number. In this slide, we present the solutions for the first primes of the form 6n plus 1, both as x squared plus 3 times y squared and as twice the sum of one triangular number plus 3 times another one plus 1. It's easy to see that the first triangular number satisfies the divisibility criterion. We can apply the same procedure for primes of the form 10n plus 1, which can be represented as a square minus 5 times another square. To satisfy this representation, the factor in brackets must be divisible by 5, requiring the first triangular number to be divisible by 5. Since all integers are congruent to plus minus 1 or 2 modulo 5, we only need to rule out x could have plus minus 2 as a residue. Once this is done, we establish that plus minus 1 works as a residue modulo 5, given the index of a triangular number. In this next slide, we present the solutions for the first primes of the form 10n plus 1, confirming that the first triangular number is divisible by 5, as its index is either a multiple of 5 or has plus minus 1 as a residue modulo 5. We can apply the same procedure for primes of the form 14n plus 1, which can be represented as a square plus 7 times another square. The difference with the previous cases is the lack of a factor 2 multiplying the sum of triangular numbers, and that their indexes are 2a and 2b. When expressed as x squared plus 7 times y squared, we can identify that x is not congruent to plus minus 2 or 3 modulo 7, following the procedure for previous cases. Thus, x must be congruent to plus minus 1 modulo 7, something that's satisfied by the index of the first triangular number, therefore ensuring that 14 divides the factor in brackets. In this slide, we share the solutions for the first primes of the form 14n plus 1, confirming that the first triangular number is divisible by 7, as its index is either a multiple of 7 or has plus minus 1 as a residue modulo 7. The last case are primes of the form 30n plus 1, which can be represented as x squared plus 15 times y squared. What's different here is that the identity includes a factor of 1/2, while the indices of the triangular numbers are multiples of 4. When mapping the identity in terms of x and y, we verify that x must be congruent to plus minus 1 or 4 modulo 15. To establish this, we address the divisibility criterion for 15, which, being composite, requires considering three cases. 15 divides one of the two factors of the first triangular number, or 3 divides the first and 5 the second, or vice versa. In this slide, we share the solutions for the first primes of the form 30n plus 1, confirming that the first triangular number is divisible by 15, as its index is either a multiple of 15 or has plus minus 1 as a residue modulo 15, or that the two factors of a triangular number are divisible, one by 3 and the other by 5. To end section 2, we present three general polygonal number identities yielding prime representations. Using the formula for polygonal numbers, we can identify a first general identity that connects the difference of polygonal numbers with the difference of squares, involving coefficients of the form 4k plus 1. When k equals 1, we recover the previously covered primes of the form 10m plus 1. When k equals 3, the identity provides a representation for primes of the form 26m plus 1, involving the difference of pentagonal numbers. The other primes that can be expressed as x squared minus 13 times y squared are of the form 26m plus minus 3 and 26m plus minus 9. Using a similar formula for polygonal numbers, we can identify a second general identity that connects the sum of polygonal numbers with the sum of squares, involving coefficients of the form 4k plus 3. When k equals 0, we recover the previously covered primes of the form 6m plus 1. When k equals 2, the identity provides a representation for 11 and primes of the form 22m plus 1, involving the sum of pentagonal numbers. The other primes that can be expressed as x squared plus 11 times y squared are of the forms 22m plus 3, 22m plus 5, 22m plus 9, and 22m plus 15. Using the formula for polygonal numbers, we can identify a third general identity that connects the sum of polygonal numbers with the sum of squares, involving coefficients of the form 2k plus 1. When k equals 2, the identity provides a representation for primes of the form 20m plus 1, involving the sum of pentagonal numbers. When k equals 3, yields a representation for 4 times primes of the form 14m plus 1, the ones visited before, but this time involving hexagonal numbers. That's all, folks. Thanks for watching. If you enjoyed this content, don't forget to give it a thumbs up, leave a comment with your thoughts or questions, and share it with anyone who might find it valuable. Your support means a lot.